Good morning, everyone. Welcome to today's webinar. We are going to look into the topic of life cycle analysis performed on an automobile component. A brief outline of the topics to be covered. The goal is to perform life estimation on an automobile component through simulation approach. To get to the goal, we first start with doing experimental model analysis on the component, and this is done to calculate the damping values, and then this input is used in the finite element model of the component, and we perform analysis, and the results are used to arrive at the value of the life of the component. This slide shows a description of the component. So this is where the part fits in a motorcycle, and this shows the experimental setup while doing experimental model analysis. So the experimental setup, in addition to the component, consists of three instruments. One is a hammer, and the hammer is shown in this picture here. It weighs about 160 grams, and it has a sensitivity of 11.2 millivolts per Newton. It converts the force of impact that is given to the component in the form of a voltage, and the hammer has a sensor which can measure forces up to 444 Newton, and it has a resonant frequency about 22 kilohertz. When you take the component and you give an impact to the hammer, the component vibrates, and the vibration response is measured using an accelerometer. And the accelerometer weighs about 3 grams, and it has a sensitivity of 5 millivolts per G. The measuring range is nearly 1000 G, and resonant frequency of 55 kilohertz. The data from the hammer and the accelerometer are signal conditioned and digitized, and is recorded in a computer, and this is done using this data acquisition card, which consists of 4 channels with a sampling rate of 50 kilosamples per second, and these are channels which can connect to IEP-enabled sensors. So when you take the gearbox and you give an impact to it, the time series of the measured signals looks like what we see in this graph here. And when you do some analysis and compute the frequency response functions, the amplitude of the frequency response function would look like what we have in this picture here. So in the measuring range of up to 1 kilohertz, there are 2 resonant frequencies that are captured. One is at 584.61 hertz, and the second one is at 937.71 hertz. How are we going to use this? The goal of this experimental model analysis before doing life cycle estimate is to be able to arrive at the life of the component, and to arrive at the realistic life estimate for the component, we need to have an accurate value of damping, and that is where the frequency response functions are used. So to calculate damping, we use a parameterization technique. It's also referred to as curve fitting, and there are various methods for doing it. In this particular experiment, we analyze the data using RFP, which is rational fraction polynomial curve fitting, and this shows the curve fitting procedure performed on the first resonant frequency around 584 hertz, and the second resonant frequency around 937 hertz. So using the curve fitters, we estimate the damping, and the model that we use for damping for this component is this 2-parameter or alpha-beta model. So alpha works out to be 18.8, and beta is 0.0144. Now let's move on to how do we use this to get to our goal of actually estimating the life of the component. So the first thing is studying the response of the component for real loading conditions. And the way we would do it is through simulation. So the first step is to build a finite element model which represents the component. It's made of aluminum alloy with an Young's modulus of 70 gigapascal and density 2,600 kilogram per meter cube and Poisson ratio 0.25. and we build a surface mesh of the component. The elements have a thickness of 1.16 millimeters, and after complete discretization, the model has about 7,000 nodes and 3,500 elements. The analysis that is performed is transient analysis. We apply a sinusoidally varying load with a frequency of 50 Hz and amplitude of 100 Newton. And the point where the component is fixed to the motorcycle through bolted joints, they're all marked by these fixed boundary conditions, the finite element model. This shows some of the parameters of the model. We did analysis with damping and without damping to capture the estimate and see how does the value of damping impact the results that we obtain. So the analysis type is transient analysis, and the method that we use is direct transient with 100 substeps and a time increment of 0.01 seconds and an output interval of 1 second. And in the model with damping, everything remains the same. We incorporate the alpha, the mass matrix multiplier, and beta, the stiffness matrix multiplier. The alpha is 18.8 and beta is 0.0144. Now the point where the maximum stress occurs is located, and we take the von Mises stress value from this point, and this is cyclic loading, and this shows the von Mises stress plots without damping. And naturally, when you incorporate damping, the stress values will go down, which is reflected in this plot for the model built with damping. Now we compute the alternating stresses for the model without damping and with damping, and the maximum von Mises stress, minimum von Mises stress. And the way you calculate alternating stresses is maximum minus minimum over 2. We repeat that for the model with damping. There is a order of nearly 5 to 6 times difference in the value of the stress is calculated for this model. And then from the alternating stresses, how do we compute the life cycles? This shows the plot of alternating stress against the number of cycles. As is expected, when the stress keeps going up, the life expectancy keeps coming down. So in this case, the stress that we compute is somewhere in this zone, and from this we can map the life of the component. So with damping is a realistic model. With damping, we get an alternating stress of 0.68 megapascal, and this is less than 82.7 megapascal, and so obviously, and life of the component is estimated to be greater than 100 million cycles, which is like infinite life condition. So essentially, the model of damping can affect the life estimated for the component. So it is critical to estimate damping, and this is done through experimental model analysis. Thank you for